Hello everyone, I'm honored to attend this conference. My name is Huayu. My paper is Coordinated Beamforming Optimization with Interference Suppressing for Mass MIMO Systems. Now I will explain my paper in the following aspects. First of all, introduction. Recently, mass MIMO technology is widely regarded as a key technology for higher data rates, as shown in Figure 1. This is mass MIMO system. The performance of mass MIMO systems has been well researched. Number 2, coordinated beamforming. Coordinated beamforming is more effective and plays an important role in improving energy efficiency, especially in mass MIMO systems. However, the energy efficiency and the throughput of mass MIMO system is sensitive to palette reuse factor and interference. Therefore, we propose dynamic division of area coordinated beamforming algorithm to suppress the interference and improve system performance. Next, it is abbreviated DDA coordinated beamforming algorithm. System description. About system model and channel model, I will only brief introduction. We consider the downlink of a massive MIMO system. Base station is equipped with M antennas, serving K single antenna users. K is less than or equal to M. The channel model. This is represent the instantaneous propagation between the mass antenna of base station I and K users in cell J. And this is channel metric from base station I and related K users. And this is small scale feeding vector between the I base station and K users in I cell. And this is channel feeding metric. And it is path loss from base station I to the user's K in cell. This is the distance from base station I to the edge user K in cell I. Alpha is the path loss exponent. And this is greater than 0 is the channel attenuation. The following is DDA coordinated beamforming algorithm. The user of an local cell in the cooperative range is defined as the extended cooperative user. This is the extended cooperative users. We can see that they are most vulnerable to interference from the local cell. Therefore, the density function of the distribution can be expressed as follows. They are the nearest distance from the base station to the edge of the cell and from the base station to the edge of the cooperative area. X represents distance between base station to users. The following is comparison with zero forcing algorithm. We can see that all spatial degrees of freedom are used for user multiplexing in traditional zero forcing algorithm. However, some spatial freedom is used to suppress interference of cell edge users in the proposed DDA coordinated beamforming algorithm, and which the base station increases the transmission power so that user in the cell cause less interference to neighboring cell users. Inter-cell interference can be effectively respected. Next, results and discussion. In this part, first, the algorithm based on cooperative area is studied. Meanwhile, the respective cooperated area division algorithm for the best energy efficiency and throughput are obtained, and the algorithms are compared and discussed. Afterward, we compared the performance of proposed algorithm and traditional algorithm in energy efficiency and throughput. Finally, we analyze the robustness of proposed algorithm, considering the impact of CSI error and pellet reuse factor. The energy efficiency and throughput is defined as follows. This is the downlink user's rights, and this is the power consumed by power PAS, and this is circuit power, and this is closed distance from the base station to the edge of the cooperated area. The simulation results are as follows. Figure 4 shows the energy efficiency comparison with different number of base station antennas and different cooperated area. We can see that the energy efficiency only slightly increases after the sidelines of the cooperated area exceed 1,100 meters, which reaches the optimal when the sidelines is 1,400 meters, due to the non-uniform user deployment and hardware circuit power limitation. The energy efficiency does not increase in proportion to the size of the cooperative area. Figure 5 shows the throughput with different cooperative area and the number of antennas on the base station. Different from the trend of energy efficiency, the throughput increase as the sidelines of the cooperative area. This is because the proposed algorithm suppresses the interference at the cost of increasing the total PA power. So, the energy efficiency cannot increase indefinitely. Therefore, a large cooperative area should be selected to increase the throughput with the similar energy efficiency to further improve the system performance. As shown in Figure 6, the energy efficiency varying with the number of antennas under difficult pellet reuse factors 1, 2, and 4. Note that the influence of pellet contamination is serious. The proposed algorithm maintains the higher energy efficiency than the traditional algorithm. Moreover, the more serious pellet contamination is, the more obvious the improvement. And in Figure 7, shows the variation of system throughput and different pellet reuse factors. It can be seen the throughput of system is reduced obviously when the pellet reuse factor is reduced, especially for the traditional algorithm. However, the system throughput of the proposed algorithm is always higher than zero forcing algorithm. Figure 8 shows the effect of imperfect CSI on the energy efficiency with the traditional algorithm and the proposed algorithm, which as a function of the number of base station antennas. We can say that the system energy efficiency has deadline for both the traditional and proposed algorithm. The most antennas are exploded, the more obvious the advantages of the proposed algorithm. And figure 9 shows the change in system throughput as the number of antennas, with and without CSI errors. The system throughput with the proposed algorithm slightly decreases with the influence of imperfect CSI. That is, the CSI error has relatively small influence on the system throughput than energy efficiency. Furthermore, the system with proposed algorithm has very stable throughput. The last part, conclusion. In this paper, suppress interference and improve the energy efficiency are explored with considering the neighboring edge users at the cell edge. The proposed DDA-coordinated beamforming algorithm by suppressing interference is proposed. In this paper, analyze how to select the cooperative area to maximize energy efficiency in multi-user MIMO systems. In contrast to existing work, we suppressed the interference of cell edge users to improve network performance by exploiting and using the spatial degrees of MIMO systems. The algorithm focuses mainly on users at the edge of cell that are most vulnerable to interference. That is, suppressing the interference of excited cooperative users. By adjusting the cooperative area, we have obtained the optimal energy efficiency and throughput with the proposed algorithm. Therefore, we can deploy the base station antenna according to the number of sub-users and improve the performance of system by selecting an appropriate cooperative scheme and cooperative regions. Finally, we explored the effect of palette review spectrum and the CSI errors on the system performance. Numerical results shows that the proposed DDA-coordinated beamforming algorithm is more robust to palette contamination and CSI errors, and more suitable for MIMO systems. That is all for my paper. Thank you for your attention.